So this is the lab lecture for theory and calculations to go with the determination of the dissociation constant for a weak base. So hopefully, not surprisingly, this lab calculation is going to be very similar to the dissociation constant for a weak acid. The differences between these labs are that in the previous lab, it was a strong base, sodium hydroxide, reacting with an unknown weak acid, which we just called HA. For this lab, it's an unknown weak base, so we're just going to call that B, okay, reacting with a strong acid of hydrochloric acid, okay, and when this reacts, we're going to see the base accept its proton. So this is what we're going to see now. The chloride is neutral, okay, so it's not reacting. The other way we could look at this if we just said, oh, base, weak base, and we know the 7 strong acids are equal to H3O plus, right? So if we look at it that way, HB plus will be what happens when the acid dissociates, donates its proton, and the base accepts it, and we're left with H2O. Either one of these equations are the same thing because HCl is equal to H3O plus. Okay, so for this lab, titrations will have been done 3 times where there are pH values at various points along the titration. In trial 1, it's every 1 milliliter of hydrochloric acid, the pH is measured. In trials 2 and 3, it's every 1 milliliter until you get close to that equivalence point. Then it was 0.1 milliliter increments. So the data table, full of lots and lots of values, what we're looking for to help identify the equivalence point. So with the weak acid lab, it was for a really big jump in pH. Well, for the weak base lab, so here's my pretend, data table. It's going to be a really big drop in pHs because the weak base starts out basic and we're adding acid to it, so the pH is slowly decreasing until it suddenly decreases. So let's go with at 21 milliliters and at 22 milliliters. Maybe I had a pH at 21 of 10.33 and a pH at 22 of 6.49. Okay, so big drop, big drop. Okay, so that's showing our equivalence point. Our equivalence point will be the volume of HCl at the end of the big drop, so with the smaller number. So we're looking for the 2 data values with the biggest change in pH for trial 1. So our equivalence point in my pretend example in this one would be 22.00 milliliters. Now to help visualize this, you are going to be graphing, making a graph for each trial with the volume of HCl in milliliters on the X and the pH on the Y, and it's going to visually look something like this. Okay, and that represents that equivalence point. Okay, then the half equivalence point in the last lab, we determined that by taking the volume and dividing it by 2, sames. Okay, so we're just going to take the volume at the equivalence point, divide it by 2. And we know that the pH, or actually, let me rewrite this. The pKa is equal to the pH at the half equivalence point. So once you've determined your half equivalence point, so like here, you're going to go back in your data and look at 11.00 milliliters and see what the pH is at that spot, and that's going to be equal to the pKa. So number 3, the pKa, that's coming by looking at your data. Again, in trial 1, it's going to be much easier than in trial 2 and trial 3, because in trial 2 and trial 3, your equivalence point's probably not going to be a perfect whole number because you're doing those 0.1 milliliter increments. So you might have to do some estimation, like maybe your equivalence point is at 10.7. You're like, well, I didn't make a measurement at 10.7. I made a measurement at 10 and I made a measurement at 11. So you're going to have to kind of estimate what you think it would be at 10.7. And again, here's where your graph can be helpful. Okay, so we're getting our pKa by finding the pH at whatever your half equivalence point is. And that's glorious, except this time I want the Kb. At the end of this, I want the Kb. Okay, so some equations from lecture is this beautiful equation. Now I'm just going to take the negative log of this entire equation. And when I do that, the negative log of 1.00 times 10 to the negative 14th is 14.000. The negative log of Ka, I'm going to abbreviate as pKa. And the negative log of Kb, I'm going to abbreviate as pKb. So after you've determined your pKa number by looking at what the pH was at the half equivalence point, you can substitute it into this equation to solve for the pKb value just using subtraction. And that's how you're going to get number 4, pKb. And it does say show the calculation. Your calculation is not terribly difficult. It's subtraction. But you still need to show that. Okay, so let's say my pKb is 10.97. Okay, the next number underneath that is kb. So just here's the equation for pKb and how it's related to kb. Okay, so just a reminder. The number of decimal places over here is going to be equal to the number of sig figs inside of the log. So like in this pretend number, I have 2 decimal places, so my kb needs to have 2 significant figures. So you're going to take your pKb and substitute it in here to solve for your kb, solve for the average, solve for the standard deviation. So we have 2 jobs in this lab, and that's to find the kb value for the weak base and then to find the molarity of the weak base. Okay, so this is how we find the kb value. Now when we switch over to the other page, we look at number 8. Number 8 says volume of unknown weak base. Well, in the lab procedure, you were told to pipette 25.00 milliliters using a 25 milliliter pipette of the weak base into each beaker before you do the titration. Now you're also going to be given the molarity of hydrochloric acid because it will have already been standardized by Katrina and we're just going to use that number. So we'll know the molarity of HCl as well. Now, at the equivalence point, only we can use this lovely shortcut relationship between acids and bases as long as it's a 1-to-1 mole ratio. And luckily for us, looking back at the balanced equation from up here, everything's a 1-to-1 mole ratio. So, but this only works at the equivalence point. So your volume of weak base for everybody is 25.00. We don't know the molarity of the weak base. That's our question mark. Okay. The molarity of the HCl will be given to you. So, so I'm just going to write given. And that's what's going to be written down on number 9. That's the given value. And then the volume of the HCl that you're going to use is going to be the equivalence point volume because this equation only works at the equivalence point. So you will plug in the molarity of the HCl, the volume of the HCl at the equivalence point. We don't know the molarity of the base. And you'll plug in 25.00 for the volume of the base. Do the algebra necessary to solve for M2. Get your molarity for number 10 for trial 1, 2, and 3, unrounded and then rounded. Calculate the average, calculate the standard deviation, and calculate the relative standard deviation. And at that point, we now know both the Kb value of the weak base and the molarity of the weak base. Again, very similar calculations. The biggest difference between this lab and the previous lab was this step right here, where we had to convert the pKa into the pKb. In the last lab, we took the pKa and just directly turned it into the Ka, and then we were done. But since we're working with a weak base, we care about the Kb, so we had to convert it over. This relationship is true whether or not we have an acid or a base because of the Henderson-Hasselbalch equation. Now, in the introduction, it also shows the other version of the Henderson-Hasselbalch equation, which solves for POH and involves Kb, or pKb, but our equipment measures pH, not POH, so we're using this one. Now, outside of these calculations, there are also the post-lab questions. Now, number 2 is a 4-part problem between the weak base methylamine and nitric acid. So just to help with this, you're going to be referring back to that beautiful table from lecture about strong acids only, strong bases only, weak acids only, weak bases only, strong acid and strong base, weak acid, weak base, strong base, weak acid, that whole thing. Okay, but what I want to do is give you the balanced chemical equation for number 2 to start with, and then you're going to do all the math for it. So if we want to write it out using the chemical formulas, I'll do that, and then I'll also show you how to do it, without using the official chemical formula. So this is the weak base, and it is reacting with HNO3. Okay, so this is a weak base. This is a strong acid. So they're going to behave as acids and bases. So the acid is going to donate its proton and the base is going to accept it. So we're going to see NH3 NH2 become CH3 NH2 becomes CH3 NH3 plus, that H plus is hanging out and being accepted by the base, which just leaves nitrate alone. Well, what we know from our lecture is that cations and anions, we know that positive charges are acids except for that list of exceptions. This is not one of those exceptions. Negative charges are bases except for that list of exceptions, and this is one of those exceptions, making this a weak acid and this neutral. If you don't want to write it out like this, you can just use the capital letter B to stand for weak base and H3O plus to stand for strong acid. Okay. And what's going to happen is that H3O plus is going to donate its proton, making a weak acid. And oops, and what we're going to be left with, H3O plus donated its H plus, leaving H2O liquid. That's neutral. So we've got a weak base, a strong acid, and a weak acid. Okay, so use one of these two, whichever one you like better, as your balanced equation for part A, part B, part C, and part D, and number 2 for the post-lab questions. Now, number 3 and number 4 are also things that go along with the lecture content with this material. The only thing I want to make sure you recognize is in number 3, we're reacting HBr, which you can figure out what type of acid that is. And then we're reacting calcium hydroxide, which you can figure out what kind of base that is. But calcium hydroxide, it's a little special because there's 2 hydroxides. So this is one of the strong bases with 2 OHs. Okay, and its relationship with hydroxide, when we were memorizing the 8 strong bases, was this. We have to take the molarity of a strong base times 2, and that's equal to the molarity of hydroxide. So what I'm telling you is make sure you apply that. So yes, you're given the molarity of calcium hydroxide, and that's awesome. But you're going to have to do something to that molarity before you can actually do the calculations for this lab. And what that something is what I just outlined in a rectangle that we learned in the previous chapter. Okay. So again, these post-lab questions, yes, there's 4 of them, but number 2 has 4 parts. So they're time consuming and they're good practice for the lecture content. So let me know if you have questions about this.